Well, good morning. Last time on Monday, we described a glass tank and we looked at a post-mortem study of a glass tank roof or crown, which was a silica brick. So I just wanted to do another post-mortem study on an AZS brick in a glass melting tank. And then we have mineral processing, which are rotary cement kilns and a lime kiln, the vertical lime kiln. And then I have some post-mortem studies on these type of refractories, which would be an alumina refractory, an MgO refractory, and a spinel refractory. So this is an AZS refractory from a glass tank wall. And basically on all these SEM studies, we try to compare a new microstructure to a used microstructure and see what the difference is. And sometimes we don't have new refractories. We try to look at the cold face or somewhere behind the hot face to try to find an original microstructure. But this is 1 inch behind the hot face of an AZS refractory. And then we had a cold face here. So we did an XRF-ICP to get a bulk chemistry. So this is the as manufactured chemistry of this AZS brick. It's about 44% alumina, about 30% zirconia, and about 23% silica. And this is 1 inch behind the hot face at 35X. The SEM EDS chemistry is about 48% alumina, 26% zirconia, and 17% silica. In red here, there's Na2O and CaO. That's infiltrated the refractory from the glass. So it's a soda lime silica glass. And then same location, 1 inch behind the hot face at a higher magnification. This is a pretty typical microstructure that we've already described. The white areas are the zirconia. So there's zirconia crystals, the larger white areas, and then the smaller white dots are the precipitates in the alumina, and that's the eutectic microstructure we described. So these white dots are zirconia in an alumina matrix. You can sort of see the outline of the alumina crystal. It's a little darker gray than the glassy matrix. So here's a dark gray alumina crystal. This portion didn't have any precipitates, but it's basically 100% alumina. And then the glass is there for the cushion for the monoclinic to tetragonal zirconia transformation. The glass is rich in silica. There's some alumina. Some zirconia is dissolved in that. But it's rich in Na2O, almost 10%, and CaO, almost 6%. So that's infiltrating through the glass matrix. This is another 750X magnification. And this one, you can more clearly see the alumina crystals with the zirconia precipitates. Here's another alumina crystal. And then in between the alumina crystals and the zirconia crystals are the glassy phase, the matrix. So we can map the different elements. This is aluminum and turquoise. So you can see where the alumina crystallized. The black holes are where the precipitates are. And then you can see some alumina also in the matrix, in the glass. And the black is where the zirconia crystals are. So the orange color here is ZR. So you can see the larger crystals and then the precipitates in the alumina. And then the purple is silicon, Si. So that's the glassy matrix between the alumina crystals. Here was an alumina crystal, and these are the zirconia crystals. So that's the matrix. The matrix contains the calcium and the sodium also. So switching right at the hot face, the microstructure looks quite a bit different. Again, this is the unaltered or cold phase bulk chemistry, alumina, zirconia, and silica. And there's still some sodium there and a little bit of calcium. But the chemistry on this micrograph here is about 52% zirconia, 29% silica. Now the alumina is highlighted here in red because it dropped to 6.7% from 44%. And then the Na2O is up to about 5 and the CaO is almost 4. So the alumina in the material has been attacked and depleted. So this is a 750x magnification of the hot face. And now there's only two phases here. There's the zirconia, the white or very light gray crystals in a glassy matrix. And that's about 60% silica, almost 8% lime, about 8% Na2O. And you can see how low the alumina is,
So we're
maybe
gonna
11%. And the zirconia is partially dissolved in the glass. So the alumina crystals are gone and they're in the glass and it's been depleted. So the turquoise is Al, the aluminum. It's totally in the glassy phase. The lime in this yellow color is primarily in the glass matrix. The blue is sodium, that's in the glass matrix. And the black type holes are the zirconia, they show up quite well. The silicon is in this purple color here. Again, it's the matrix. And then here are the zirconia crystals in orange. So the structure has completely changed at the hot phase. So back in the interior, somewhere behind the hot phase, there's a transition zone. So there's a thermal gradient in these sidewalls. So at some point, there's a freeze plane um, where the sodium and calcium diffusion stops. And that's right along this transition zone. So here's the interface between the original refractory, unaltered, and then the altered refractory. So the temperature profile is such that there's a freeze plane here when basically stops the reactions in the interior of the brick. So you can see that the difference in the microstructure. This is zirconia in a glass phase, and this is zirconia and alumina plus the glass phase. So if you map Al, you can see the distinct interface here. These are in this turquoise color, the alumina crystals. And then alumina now is this lighter turquoise color, but it's in the glassy matrix. You can see where the silicon infiltration stopped. So the purple is Si. And also the calcium infiltrated up to this interface. So it's calcium rich here, silicon rich, which is what you'd expect. Calcium's, silicon and sodium are in the glass. And this one doesn't show up as well, but the blue here is Na, and here's the interface, and there's less of it here. And then the ZR or zirconia composition was enriched because we lost the aluminum oxide. So the orange color here is a little bit brighter on this side of this interface than on the side with the original refractory. So you can try to use phase diagrams. It's not that easy when the system's so complex. but this is SiO2, Al2O3, and Na2O. So that's one of the components that infiltrated the refractory. So I normalized the three components to add up to 100%. And that composition falls right around here. Uh, that's near the Albite phase field. It's a low melting material. And if you look around here at the different eutectics, then maybe there's a peritectic also over here. You can look at the temperatures, they're all around 1,000. This one's around 700 degrees C. So you're in this area of the phase diagram, you have a low melting material. And I think I mentioned when we talked about phase diagrams, there are thermodynamic programs you can buy. I think I had them emailed to everyone that you can put in all the components and see what you expect as a result, see what the low melting phases are. But there is definitely some low melting glasses in this matrix of this material. So I thought I'd mention rotary cement kilns and lime kilns because they produce minerals, and the cement kiln obviously produces Portland cement. The charge is pretty simple: limestone, the calcium carbonate. This is the clay, the aluminosilicate that's hydrated, and silica. So this cement kiln is a large, long cylinder. It rotates and it's tilted at a slight angle. So at the high end, the raw materials are fed in, and as this rotates, the materials move down into the hotter zones, and then you have reactions to form Portland cement, and they take place at about 1,500 degrees C. And then this is a sintered product known as clinker. It exits the hot end of the furnace. So you end up with Portland cement. It's primarily a tricalcium silicate and a dicalcium silicate. Those are the phases that hydrate. You also have 3CaO Al2O3 and 4CaO Al2O3 Fe2O3. These are present in minor amounts, but they can also hydrate. So this is what the a cross section looks like. This is a long cylinder. It's tilted and it rotates. So this is the cold end. The feed comes in here. So there's a cold zone and intermediate temperature zone, and then the hot end here, the hot temperature zone. So this is the burner. So there's a flame here that produces the high temperature in this region and much lower temperatures towards the cold end. So as the charge travels down here, it reacts and forms the cement compounds, and then it exits right here at the hot end. So how this is zoned, the primary issues are thermal shock and abrasion. So this is the cold end. These are just chains that hang down to help prevent clinker buildup. So this is the preheating zone, the low temperature area. That's usually a Super Duty fire clay brick. And then as you get into the intermediate temperature region, where the material is calcined, where you decompose the carbonates and dehydrate the clay, you might have a higher alumina brick. And then towards the hot region, where you start sintering the charge, that's usually an MgO alumina brick. That's a spinel type material. And that's been replacing the mag chrome bricks because of the issues with health issues with chrome. But either MgO alumina spinel type brick or mag chrome brick in this region. And the discharge at the hottest zone may be a MgO alumina spinel brick or a high alumina brick, very high alumina. So the idea here is the raw materials go down, from the cold zone to the hot zone. And they try to build up a clinker uh, at this interface, a coating of the clinker to work off of the coating instead of off of the refractory because of the abrasion issues as this material turns down. So in the hot area, it's desirable to build up several inches of the clinker so that you're working on that lining instead of the refractory lining. And then in a vertical lime kiln, the charge is simply calcium carbonate. And here you can mix carbon in the form of coke with the calcium carbonate, and that can be a fuel source similar to a blast furnace. So the limestone plus the carbon source is charged at the top of the cylinder. The material moves downward, and the highest temperatures are about 1500 degrees C. And then you end up with a sintered calcium oxide product. So in this vessel, you're just decomposing calcium carbonate, forming CaO, and you're liberating CO2 gas. If you have a carbon fuel source, the carbon reacts with the oxygen, forms CO2, and that's your heat source. So this is a vertical lime kiln, how it's zoned. Similar to the cement kiln, you have thermal shock issues with the cold charge coming in, and as it moves down the furnace, you have abrasion issues. So the top here is usually a high alumina brick. That's where the material is charged into this furnace. Then the working lining is either MgO or MgO chrome. Lime is a basic material, so it's very compatible with basic refractories like MgO and MgO-Cr2O3. The backup lining is some type of high alumina. It may be a brick or a castable. And then there's another backup lining, which is an insulating lining. So this backup lining is really the safety lining. And the insulating lining is an IFB or a castable, maybe an alumina silica material. So I picked 3 different post-mortem studies in a cement kiln. This one is for the high alumina brick. I also did one for the MgO brick and one for the spinel brick. So in this case, I pretty much just had a hot face. That's what was left after this furnace went down. So if you do the chemistry at low magnification at 20x, the alumina content's about 60%, the silica about 16%, and the lime and potassium oxide are from the charge. They're not part of the original refractory. They've infiltrated at the hot face. So if you look at the aggregates here, they're at least a 90% alumina aggregate. The balance, there's some SiO2, some K2O, probably infiltrated from the charge, and a little TiO2. There's also some P2O5. I'm not sure, maybe there was some phosphoric acid here as a bond in the matrix, because little P2O5 shows up over here. So this might have been a partially phosphate bonded high alumina. But you pick up a lot of calcium and potassium oxide in the matrix. So the alumina content is down to about 35%. The silica is up, and that's from the charge, up to 25%. Plus the lime is from the charge, about 15%, and the potassium oxide is about 14%. So that's in red here is what's contaminating the refractory. And also, since the charge has silica in it, that also infiltrates the refractory. You can also see there's a lot of micro cracking in this material. So if you map in blue here, the aluminum, you can see the coarser aggregates and the finer aggregates. Uh, the SiO2 in yellow or orange here is in the matrix between the coarse aggregates. So this black area was the coarse aggregate. So it's in the matrix. And you can see how the lime here in yellow is infiltrating into the refractory. This is right at the hot face. There's quite a bit of lime in the matrix, but it's diffusing in. Um, it's mostly concentrated at the hot face as there's a temperature profile, so the diffusion slows down as you go into the refractory. Potassium is a lot more mobile than the calcium in purple here. So the potassium oxide has really diffused into this refractory in the matrix. So this is a new sample that we also received and did a bulk chemistry by XRF and ICP. So this was a 70% alumina refractory, and the balance being primarily silica. And one thing down here, we didn't pick up any P2O5, so it may not have been a phosphate bonded material. Maybe this is coming from the charge. So this is the used bulk chemistry. You can see the alumina and silica contents are down. This is right at the hot face, and then the lime and the K2O is increasing. And the aggregate, greater than 90% alumina, and very little CaO or K2O. So the aggregate is very stable and resistant to the attack, but the matrix, again, the alumina is down. The silica is similar to the original silica, but it's some of this is coming from the charge, and the lime again is up, and so is the potassium oxide. So there's a great deal of CaO and K2O diffusing into this refractory. And again, you can try to look at some ternary phase diagrams. This is alumina, silica, and K2O. The composition is somewhat approaching, the overall composition is somewhat approaching mullite. So I picked a point here and went across to the normalized silica K2O and alumina content, which is over here. It's heading towards this field of lucite, which is a low melting material. And then I did the same thing with alumina, silica, and lime. I started at mullite, and this composition is shifting in this direction to this other low melting phase field, galenite. So I found the phase diagram for silica and orthite, which is anorthite's next to galenite here, same components, and then lucite, and put on where the composition is falling. It's falling in this region here. So if the hot face is higher than 1400 degrees C for this refractory, you're going to have liquid formation. And the hot zone's higher than this in these furnaces. So trying to use phase diagrams to figure out where these liquidus curves are, where the liquids form. So this is an MgO brick from another cement kiln. And this is the actual MgO refractory right here. This interface is the hot face of the refractory, and then this is 3 inches thick. So this is 3 inches behind the hot face. And I mentioned they like to build up a clinker layer, which is this sintered cement material, to build that up on the hot face. And then this is the new hot face. So they're working off of this region. So this is about a 6 or 7 inch thick clinker layer adhered to the MgO refractory. So that's kind of the ideal way to run a cement kiln. So we can look 3 inches behind the hot face, and the bulk chemistry here by the SCM EDS is about 87% MgO. There's some silica, some lime. This MgO has quite a bit of iron, about 7%. And MgO bricks with high iron contents um, tend to allow the clinker to adhere to that surface. So these iron contents are there deliberately. We also picked up SO3, a sulfur oxide compound, at a little more than 1%. So the sulfur is coming probably from the charge. So if you look at the aggregated matrix chemistries, here's a aggregate of MgO. It's about 90% MgO and almost 8% Fe2O3. It also has picked up a little bit of sulfur in the form of SO3, about 1/4%. And then the fines in the matrix. The matrix is the same, pretty much. It's almost the same here. This is 90%. This is 87%, 7 or 8% Fe2O3. And there's a little more lime in this material and a little more silica. And some additional sulfur is also present. So that's 3 inches behind the hot face. If you map that, the blue is the MgO. You can see a coarser aggregate and the finer aggregates in the matrix. The iron is pretty uniform, whether it's in the matrix or the aggregates. The matrix was probably made by grinding the coarser MgO aggregates into the fines for the matrix. That's why the chemistries are the same. The lime is in the matrix in this bright green. And associated with the lime is sulfur. So it's probably a calcium sulfate forming 3 inches behind the hot face. And if you look at these coarser aggregates at a higher magnification, 500x, these are the individual MgO crystals, and the grain boundaries in this white color here. It's easy to see the crystals because of the grain boundaries, which contain a lot of iron. So the grain boundaries are rich in iron, more than 63% Fe2O3, and the balance primarily being MgO. And then the gray area is basically close to 100% MgO. So these are the iron MgO magnesiowustite crystals that precipitate in the MgO grains. So this was the chemistry in the grain boundary area, about 63% Fe2O3 and 30% MgO. And if you put this on a diagram of MgO Fe2O3, you're right about here. And if you go up, you're in the magnesiowustite, magnesiopherrite phase field. Magnesiowustite was MgO-FeO, and then the ferrite is MgO Fe2O3. But before you form any liquid, you're at 17, 13 degrees C. So even with that much iron in the grain boundaries, the MgO can tolerate that and still be a high temperature material. So that iron was primarily added as part of the manufacturing of the MgO. So if you switch to the hot phase, this is the transition between this adhered layer of the cement clinker and then the MgO refractory brick. So the MgO refractory brick is, again, this one's about 87% MgO, and the iron is about 6% here. There's a little bit of SiO2 and CaO being picked up here, plus the SO3 is also present. And then this clinker layer, it should be a calcium silicate material, so it's about 56% CaO and almost 20% SiO2. You have some of the MgO from the refractory in that also. The alumina is from the clay that's part of the charge. And there's also some SO3 picked up, about 0.25%. And I think the chlorine that shows up is most likely from the resin that was used in the mounting of these slides. So the aggregate is a high MgO, about 95%. This one's about 95% MgO, the balance being Fe2O3. And then the matrix is still high in MgO, but there's some silica and lime present, and also SO3, about 1%. And then a higher magnification, 500x, right at the hot phase. So this is the hot phase. This is the cement clinker. The MgO crystal is about 95% MgO and 3% Fe2O3. You can see the little white spots. They're hard to see over here. They're a little better to see over here and maybe over here. Those are the iron precipitates, the magnesium-wustite. And then the grain boundary phase is rich in iron. This is 26% Fe2O3. The lime from the clinker has penetrated into the grain boundaries at a pretty high level, 23%. So if you look right at the hot phase, like this crystal here, you can see how this was probably much larger. It's been dissolved away, and you can see how it's attacking the crystals along the hot phase. So this is a ternary phase diagram. This is the grain boundary chemistry we just looked at here, right at the hot phase. It's primarily CaO, MgO, and Fe2O3. So this is a CaO, Fe2O3, MgO phase diagram. And this is a cut through that ternary phase diagram at 1500 degrees C. And this is in an air atmosphere. So there's a phase field here, magnesium-wustite plus lime plus liquid. And there's another phase field here, magnesium-wustite plus liquid. So this composition is right in this region here. So you can see you have magnesium-wustite, lime in a liquid, or magnesium-wustite in a liquid. But at the operating temperature, which is about 1500 degrees C, you have liquid phase present at those grain boundaries. So it's predicted that this white phase is probably liquid, and that's what's attacking the MgO. We also saw some sulfur in the matrix. So this gas infiltrates through the open pores, and it also helps form some low melting silicates. So the dicalcium silicate, that's the cement clinker, plus MgO, plus SO3. And we noted that the calcium and the sulfur were together in the grain boundary region. So it's forming a calcium sulfate. And then this is a low melting calcium magnesium silicate. This is muronite. We talked about this phase when we talked about MgO refractories. And then the muronite can also react with MgO and SO3 to form more calcium sulfate, plus this low melting calcium magnesium silicate monocellite, which we also talked about when we talked about MgO refractories. And then monocellite can react with MgO and SO3 to form more calcium sulfate and phosphorite, this magnesium silicate. So when you have sulfur present in the oxide form, you're most likely going to form calcium sulfate. So this calcium sulfate deposits behind the hot face in the freeze plain region, and there's an expansion, a thermal expansion mismatch, and that mismatch can disrupt the structure and cause microcracking. So there's a couple things going on here. Some low melting phases in these grain boundaries, and also some calcium sulfate deposits. And then the last postmortem I have is for a spinel brick in a cement kiln. And this is a location a half inch behind the hot face. This is what the material is supposed to be in the specification from the manufacturer. It's about a 90% MgO, and then it has about 6% Al2O3. So this is an MgO material in a spinel matrix, maybe not a complete spinel matrix, but partially a spinel in the matrix. So the chemistry that we measured was about 88% MgO, which is pretty close to 90%, and 8% alumina, and this is 6.5. So this is a bulk chemistry, and this is the chemistry over here, just at this field of view. But it's in pretty good agreement. So these aggregates here are very high purity MgO, about 98% MgO. And then the matrix regions, still high in MgO, but here's where your alumina is, 12%. So this MgO and alumina is going to form spinel. So the matrix is going to be partially spinel and partially MgO. So that's how this refractory was designed, to be a coarse aggregate of MgO bonded by a spinel type phase. So this is right at the hot phase. The MgO content is about 83%, but now we have some lime dissolved in this material, and also some Fe2O3. So the MgO content is down because of the impurities dissolving in here, and so is the alumina content. It decreases. So if we go to a much higher magnification, 200x on the hot face, you see your MgO crystals, the darker gray regions. They basically come out close to 100% MgO. And then this is the grain boundaries, this white region. So you can see the impurities are infiltrating into the grain boundaries. So this material at the grain boundaries is high in lime, about 50%, and high in iron oxide, about 23%. There's some residual alumina also present. Actually, the alumina may come from the charge also, but definitely the lime and the iron oxide is coming from the charge. So if you look at this, alumina, iron oxide, and CaO, which is what's present here, alumina, iron oxide, and CaO. If you look at that phase diagram, the ternary phase diagram, Fe2O3, Al2O3, and CaO, you end up right about here That's where that grain boundary phase is. So this is CaO, this is C3A, and this is C2F. So in cement notation, C is CaO and F is Fe2O3 and A is alumina, Al2O3. So you're right in this eutectic area, 1389 degrees C. That's lower than about 1500 degrees C, where your furnace is operating at. So this is should be a liquid phase at temperature. Keep in mind that all these polished sections are made after the refractory cools down at room temperature. So this looks like it was a liquid phase. And you can see it's starting to dissolve the smaller MgO crystals. So that's what I have on to finish up a glass tank and at least 3 examples on cement furnaces. So we have one more class next week. We'll look at some furnaces that are lined just for ceramic production and some petrochemical vessels. So that'll finish up next week. So again, thanks for listening and have a good weekend. And I'll see you next Monday for the last class. Thanks.